my screen.
Yes, let's try. Okay, so we have continuation of Volodya's previous talk on Poisson science, and
No, not Poisson, nothing.
Why?
Poisson, because I will speak about this continuation of Monge-Ampère structures.
Ah, yes, yes, excuse me.
No,
Okay,
no.
well, Volodya, let us see your screen and let us begin. Well, I ask everyone to switch off microphone if they don't need it. Well, and let's begin.
Do you hear me?
Yes, we hear you and we see you. Yes, it's perfect.
And are you able to see what I wrote?
Yes, we see what you wrote, but the image is bigger than the screen. Can you somehow?
Now it's better.
Yeah, more. Yes. Well, fine. Yes. Okay.
Fine.
Yeah.
Should I start?
Yes, please.
Okay. First of all, traditionally, thank you very much for this invitation. It's always a pleasure to be with you and always pleasure to speak. And I will continue my talk, which was stopped in December. And today I will speak about applications of those geometric structures, which I discussed in my talk in December and many times before. So this is the main source of my talk. It's my survey in the book which was published last year in Springer Berghäuser, Geometry of Monge-Ampère Structures. So I'll go to my plan today. I want again to start with my traditional excuse, and my traditional excuse now is the following. When I thought about my second part of this talk, I have realized that even speaking about second part of my long talk in December, I am unable to describe all possible interesting structures and their applications. So I had a difficult choice, and I made the choice, the following choice. Today I will describe applications mainly concerned to so-called theoretical meteorology. So I will, after a short reminder what I'm speaking about, I will describe very vaguely so-called shallow water equation in 2 dimensions and how Monge-Ampère operator appeared in this framework. Then I will describe, hopefully, elementary 2D hyperkähler triple, I mean 2D base hyperkähler triple, and two-dimensional semi-geostrophic models related to this triple. Then I will speak about 3-dimensional semi-geostrophic equations and the corresponding Monge-Ampère. That's what. Who is this?
What's the matter?
I don't know. It's not me.
Yes, that's the problem. Well, let's again try to, well, you know.
По имени Энгель влез, я его
Да.
выкинул.
Вы его выкинули. Ага. Володь, давай опять снова.
Engels, but next will be Marx probably.
Нет, Энгель.
Энгель. Ли.
Engel.
Да,
Next will be Lee. Yes, sure.
Yes. Okay, let's continue.
So sorry. Oh, well, and then at the end I will speak probably if I have time. I hope I have time to speak about so-called diagnostic Monge-Ampère equations in 2 dimensions and 3 dimensions, and very rich geometric structures. And especially I want to draw attention to people who are interested in not in our notion of integrability, but in this integrability in hydrodynamical sense, that this 3-dimensional Dirichlet-Widois equation, it's very, very interesting, very useful. I mean, useful from the viewpoint of application, degenerated in our sense equation, which is probably quite interesting from the viewpoint of hydrodynamical integrability, because this equation has identically zero Hitchin-Pfaffian and doesn't belong. So it is in some sense it is linearizable. It means that it is exactly in the stratum of hydrodynamical integrability symplectic Monge-Ampère equations. Okay, I will start. Just. So I will not remind you the correspondence between differential forms on symplectic manifold, or mainly on T star of some smooth manifold, and Monge-Ampère operators. So this correspondence, Lichagin and his students and myself many times described in this seminar. So I will remind just the notion of local symplectic equivalence between Monge-Ampère operators and Monge-Ampère equations. So we suppose that we have a local symplectomorphism of T star, which transforms one form, omega 1, and this is just n form on T star of M. This is I will restrict today to mainly to symplectic Monge-Ampère operators. So this is the n form, and this n form omega 1 corresponds to Monge-Ampère equation delta sub omega 1. And diffeomorphism, symplectomorphism transforms this n form to another n form, which corresponds to another Monge-Ampère operator, another Monge-Ampère equation, delta sub omega 2. And then we say that we have a generalized solution of the image Monge-Ampère operator, say, if the image of this L is a generalized solution of initial Monge-Ampère operator, of a generalized solution of Monge-Ampère operator omega 1 initial. So the example and the usefulness of such, sorry, just sorry, it's a catastrophe. It's very strange. Catastrophe. No. Doesn't want. Yes, it does. It does. You see, it's it goes back to the last page. Okay, so the example of such transformation, is the famous partial Fourier or Legendre transformation. So we have this picture, probably you know this picture very well. We have a Monge-Ampère operator which corresponds to this equation, Hessian, determinant of Hessian of unknown function v equal to 1. And we have the corresponding two form, dp1, dp2. So I have the case m equal r2, and I have coefficient, and I have coordinates positions q1, q2, and p1, p2 corresponding dual coordinates in t star to this q1, q2 momentum. So we have form dp1, dp2, and minus dq1, dq2. So if we have restriction of my form on the graph of some function f, so this restriction gives you a condition which is famous determinant Hessian v equal to 1 Monge-Ampère equation. I want to remind again that it was the first Monge-Ampère equation which was solved explicitly using this transformation in 1820 in a paper, very nice paper in Journal of École Polytechnique. It was written by Ampère, and that's why transformation which Ampère proposed now we know under the name of Legendre transformation. So Ampère proposed to make partial change of coordinates and replace here p1 by q1 and q1 by minus p1, and p2 and q2 rest unchanged. So we have the form omega, and the form omega corresponds, as you see, to linear equation, which is Laplace equation. Now it is just enough to take any harmonic function, which is a solution of Laplace equation, and go back to solution of the equation which was nonlinear, to Hessian equal to 1. And this is a solution given by the formula, explicit formula q2 arc sine q2 exponential minus q1 plus square root and blah blah blah. And geometrically it means that we have a graph of this function phi, and this graph is the image of Lagrangian submanifold in R4, and it is a generalized solution. It is badly projected to this. I mean, this function is defined on Q1, Q2, and this function gives you the function which is difficultly written in Q1, Q2, but solves this equation, non-linear equation, explicitly. Of course, it's a toy model, but it gives you a chance to solve many other non-trivial Monge-Ampère equation. And now I want to describe a class of examples which we have in theoretical meteorology. Just I want to tell you a few words about the models. It is a model which describe numerical simulations of weather forecast. So in fact, the only serious influence to the weather forecast has so-called troposphere. So it is a band of atmosphere up to 10 kilometers. Seriously speaking, even we can restrict to 5 kilometers. So what's happened then upper 5 kilometers, probably you can neglect it when you have a numerical simulation for prediction based on the mathematical models. And then what you do, you take this slice of atmosphere, this tropospheric slice, and then this tropospheric slice you cut by horizontal lines, such horizontal lines, and these horizontal lines slice this band of troposphere by slices which have supposedly the same how to say pressure. So this with constant pressure. So we have slice with one constant pressure, and each slice has almost 200 meters. So you have sliced 200 meters, and you suppose that all atmosphere in this slice has the same pressure. And then you sliced this tropospheric band. What's happened on the Earth? On the Earth, you also have some lattice, and this lattice is more or less square or rectangle, just 2 kilometer by 2 kilometer. So you have a parallelepiped, and this parallelepiped has a base 2 times 2 square, and 200 meters higher. And you suppose that this is a mesh, this is a, how to say, elementary cube where all parameters more or less you can give numerically, and then you make a simulation to compute a solution of some equations. Which equation you are interested in? You are interested in with so-called shallow water system. In vector form, shallow water system, it is two-dimensional system which involves so-called Coriolis rotation of the Earth. So typical parameters which we have. So here I told you about 5 kilometers, but here it is 10 kilometers. So it's more or less this slice. But it needs much more memory and much more powerful computer to if you want such numeric models. At the first stage of my work with British meteorologists, I saw these Cray computers, and I saw the programs they use. It was a huge amount of listings, and then anyway, so they have this shallow water system. And they used so-called geostrophic approximation, which is a result of this Coriolis rotation. And instead of this unknown function, they used so-called geostrophic wind vector, which is a kind of deformation. In first approximation, the geostrophic formulas gives you the same answer, supposedly, that usual shallow water equation. And in terms of geostrophic wind, in 1975, Brian Hoskins was the first who proposed to replace shallow water by semi-geostrophic approximation. Now, where Monge-Ampère is here, Brian Hoskins introduced special change of coordinates, and he used so-called geostrophic coordinates and so-called Bernoulli potential. It was his terminology. In terms of these geostrophic coordinates, big X, which replaced the initial coordinates X, and the Bernoulli potential big phi, which replaced the potential phi using this quadratic term. Semi-geostrophic equations can be reduced in very nice to very nice form. This very nice form, in some sense, Jacobian form. So it is a Jacobian of this transformation big X with coordinates x, y with respect to old x with coordinates small x, small y. And using this so-called geostrophic wind, you have the additional term here, and all this explicit expression in Jacobian form people know as a so-called potential semi-geostrophic potential vorticity. It's an important notion. We will see that this notion in future, like a Pfaffian of Monge-Ampère differential form. It was a fantastic, I would say, fantastic chance and fantastic my chance, because I became useful explicitly for this. And then this potential vorticity can be explicitly computed in terms of this transformation and gives you up to some constants. These constants, of course, in fact, they are not constants. This G is it's a gravity constant, but F, it is Coriolis constant. People in the first approximation take the Coriolis rotation with this constant parameter F. So you have a Hessian of this potential, geopotential, or Bernoulli potential, small phi, and this is a potential vorticity. Future, you will see future application of this so-called Ertel theorem, that this potential vorticity is a kind of conserved density. So you have d of material derivative of this potential vorticity equal to 0. So this equation gives you a very nice Monge-Ampère operator and a very nice Monge-Ampère equation. Of course, in practice, this potential vorticity is not so small because f is not constant, and reality is very, very complicated. But even in this approximation, you can save machine memory and machine time. So you can write also this geostrophic approximation with respect to this geopotential H. So it was geopotential H in this here, and then you have a kind of Hamiltonian representation of this system in coordinates small x, small y. Dot means just derivative, time derivative as usual, and f is our Coriolis constant here. So the system is quite simple, but you see, very nice. Okay, so this potential vorticity now I will denote by this big theta and or small psi, this potential vorticity part, and this is a full potential vorticity of the system, which includes this Jacobian term. This is also just rewritten shallow water system invariant. Okay, now what the potential vorticity really means for atmospheric dynamics. It is well known since probably 1943, during Second World War. Ertel discovered his theorem of potential vorticity conservation, and he also proposed potential vorticity, a sign of this Jacobian, sign of this Jacobian, he proposed to interpret cyclones and anticyclones. The appearance of this term, Jacobian term, means then in your model of motion of the corresponding atmospheric or hydrodynamical movement appears some rotational process. So you see on this picture, I will try to give it bigger. You have two different sign of this potential vorticity term Jacobian. This is cyclones and anticyclones, which appeared in the same day, May 14, 1992, in different areas of Atlantic. Here there is a border, and there are different atmospheric interesting phenomena. So it is called vorticity in English and tourbillonnage in French. And you will see that you can just predict such things if you able to solve Monge-Ampère equation with Hessian term. Okay, so this we discuss this big coordinates, geostrophic and semi-geostrophic coordinate. This we write this equation in Jacobian form with this geostrophic wind terms. And when you write potential vorticity explicitly with this function h, which is just transformation of your small h potential, and this transformation is nothing but Legendre transformation, you have the first Monge-Ampère equation, which I saw in this context when I came, and my colleagues from meteorological office showed me this equation. I said, oh, I know this equation, it's Monge-Ampère equation, and probably we can try to solve if we know, or we know the value of this potential vorticity, or we can compute potential vorticity if we know the data of function h. And then we started to study just geometry of this equation. And to study the geometry, we started with the study of this Legendre transformation. This Legendre transformation is quite looks quite simple. You have a toy model. This toy model, it is just a two-dimensional base Q1, Q2, and P1, P2, its coordinates in R4, complementary to Q1, Q2. And then you introduce another set of coordinates, Q1 big, Q2 big, P1 big, P2 big. P and P you just keep, but Q you add P1 and P2 to Q1 and to Q2. This transformation is immediately you can see, because it's a toy model, you can see that it is canonical transformation. So symplectic form in small coordinates equal to symplectic form in big coordinates. And if you have this function, which is p square 1 plus p square 2, which is generating function of this transformation, this function transforms to a function big V. So we just take additional coordinate to our four coordinates, considering J1. So we have a domain D in R2, and we take J1 of over D, and take a function U like a Z coordinate in this context. And then we can lift the transformation F to contact transformation, and a part of Q, we consider a transformation of this function U with the help of this generating function P1 square plus P2 square. So this transformation happily transforms, preserve the contact distribution, so contact Cartan form. And then, so this is just a remind about this contact structure. And then solution of my geopotential, it is just Legendre submanifold in J1 given by this condition. So we have Monge-Ampère representation in standard form, which Lechakin proposed in 1979. And we take the evaluation of this form on the graph, and we have the Monge-Ampère. So this was, I had to explain this to my colleagues for the first time, how to write their equation. Now we can write in terms of big Q1 and Q2 the corresponding Hamiltonian Hamiltonian system using this standard long derivative, full derivative on time, and partial derivative d over dt. And then when you write all this, you can explicitly write Legendre transformation with the function phi geopotential and the generating function q1 square plus q2 square dual to my initial function p1 p2. So we have a direct and inverse Legendre transformation between coordinates small and big, and this it is a part of so-called quartet of Legendre transformation, because you have 4 coordinates, you have quartet of different Legendre transformations, and meteorologists use this quartet to define singularities of the corresponding projections and interpret these singularities, of course, Legendre or Lagrangian singularities in terminology of Arnold, and meteorologists interpreted them like atmospheric front singularities. So they are foldings, swallowtails, and umbrellas, and different other interpretations of these 4 different singularities, for 4 different possible Legendre transformation, which people in meteorology studied in 80s without knowledge of Monge-Ampère and without knowledge of Arnold theory of singularities. Okay, now what we did. We considered, as I told you, so-called Ertel theorem, which was discovered in 1943, that if you take this Jacobian, then this Jacobian conserves if you take total derivative on time. And rewriting this Jacobian in Monge-Ampère form, of course, it is simplification for all constants which you have in semi-geostrophic context. You have this function 1 plus phi q1 q2 plus phi q2 q2. This is a result of course, the Hamiltonian form of semi-geostrophic wind plus Hessian of this potential. This is a simplification, but this simplification very, very close to reality. And if you take this condition that this expression preserves in time, you obtain 3 differential forms. Namely, you have the form big omega. This is a symplectic form in the space q1, q2, p1, p2, and also you have forms which comes from this expression. Which forms? It is easy to see that this general family of elliptic Monge-Ampère, they are elliptic because if you compute this expression, Pfaffian of this expression. This Pfaffian shows you that this is elliptic equation, and this elliptic equation gives you 3 different models if you take the different choice of constant. Now, instead of this simple theorem, we study various interesting coefficients, interesting in sense of meteorology, of course. And it is interesting that if you put here coefficient a and here coefficient a square minus c square, taking special values of a and c, you obtain various semi-geostrophic models. They are all so-called balanced or almost balanced models. And semi-geostrophic model, it is a specific choice of this. Namely, you take a equal 1 and c equal 0. So the semi-geostrophic, it is exactly this simplest expression. Then you can take a equal c equal to 1, and then you don't have a nonlinear term at all. So you have a approximative L1 Salmon dynamics. And then you can also have very strange choice of a equal to 1 and c equal square root of 3. And this model was discovered in late 90s by Mike McIntyre and Ian Ralston, my colleague from, and Mike McIntyre, now he retired. It's very, very famous British geophysicist, Royal Society member, and it is just emblematic person in the Geophysics Society of United Kingdom. So they discovered very strange dynamics, and this very strange dynamics has constant c equal square root of 3. And so we know now that all balanced models, they have this type. It follows from classification which we had with Valentin, because all these models should be elliptic, and we found from this condition constraints on this given constant, because you remember that the d over dt of this equal to 0, so this expression equal to constant. This constant can be expressed in terms of zeta, c, and the Coriolis constant. Well, what? And the ellipticity means that this ratio should be less than 3 over 2. So we have all possible models are here. Probably there are some other interesting models. Of course, this is the condition of potential vorticity uniform. It means that this potential preservation of this potential vorticity, this expression of right-hand side is constant. Very restrictive, but what to do? Sorry again, I have this problem with it. If I don't touch it, it becomes very, very sleepy. So now one can ask, okay, two-dimensional models, you more or less know how you, can you say about real three-dimensional? Because real models should be three-dimensional, not flat. So three-dimensional semi-geostrophic equation also has a very nice Monge-Ampère form. This equation appeared in 80s, and it has a Hessian term, so it's determinant of unknown function u, and Hessian with respect to two variables of
Volodya, I'm sorry. What does it mean exactly? What do you mean? Determinant of the unknown function u. What is?
I will show you just in few minutes. I will show you.
Okay.
This was equation just to show that it is equation again nonlinear and Monge-Ampère type. Of course, it is possible to treat with our approach. So we can write the corresponding effective form of this equation, and we can make change of variables. We can make change of variables to put this form as a sum of two decomposable form, and then take partial Legendre transformation. And this equation symplectically can be written in terms of Hessian equal to one of the of three nonlinear Monge-Ampère equation with constant coefficients which appeared in our classification with Valentin. And then we can find exact solution of this. This equation admits a very explicit solution, not evident, but very, very explicit, as a following function, which has the integral representation. So as a Lagrangian submanifold in R6, it is the submanifold given by the following equation. You have x, y, and then coordinates x plus y alpha, y plus z alpha, z plus x alpha. So this in 6 dimension you have this Lagrangian submanifold. So x equal to x, y equal to y, z equal to x plus y alpha, and then you have other coordinates p, q, r, dual coordinates to x, y, z. And this is a general solution of our equation Hessian equal to 1 with alpha, which is a cubic square root of this expression. So now you can use any numerical experience, any numerical simulation with solution of this equation, whatever you want. Now, where it comes? This comes from so-called this three-dimensional semi-geostrophic equation. As I told you, they were introduced by Brian Hoskins, and they considered in 3 dimension like so-called approximation of Boussinesq primitive equations. And the condition of this approximation is that, of course, that the flow momentum should be smaller than Coriolis force. And this is a condition on so-called Rossby number, which should be very, very small with respect to 1. Then this potential vorticity also exists in 3 dimension, and it is just, as I told you, a kind of symbol of cyclogenesis. It is a symbol of appearance of cyclones and anticyclones. And especially it is typical in the polar zone, in the polar fronts, in northwestern part of Atlantic Ocean. And it was Brian Hoskins, he proposed this change of coordinates, which I briefly described in 2 dimensions, but it is much more interesting to consider in 3 dimensions. And these coordinates in 3 dimensions, this change in 3 dimensions is the following. This is a Brian Hoskins transformation from 3-dimensional system coordinates to big X, Y, Z. And fantastically, that this transformation, they are explicitly also Legendre transformation, and which, of course, very easy gives us possibility to solve this semi-geostrophic equation explicitly in 3 dimensions. So we also have this small geopotential. We have these coordinates. We have these coordinates of semi-geostrophic wind. We suppose that potential vorticity is uniform, so this QG is some constant. All this constant I will not just interpret. G is a gravity constant, F is a Coriolis constant, N it's so-called Brandt-Weisshaller frequency, which I don't know exactly what does it mean. It is just a meteorological parameter, and the equation which Brian Hoskins obtained, this equation has this form, and you see that this is a small Hessian Laplacian in two variables, and it would be almost Laplacian in third variable, but the constants in front of these derivatives, they are different. Here it is Coriolis, and here it is this Brandt-Weisshaller frequency, and this should be equal to 1. It is just a normalized condition of potential vorticity conservation law, uniformity of potential vorticity. And also there is a constant theta zero, it's a theta node, it's a constant potential temperature, just come from physics of this.
Volodya, I'm sorry, but can't they be equalized if by scaling?
In principle, yes, but it is very how to say, it's very rough approximation. In fact, people like to keep some relations between this constant, but not completely normalized.
Just a remark. Thank you.
Just look what they did. They tried to keep this constant for numerical reasons, because for this, and I just give another how to say, I showed you this Hoskins transformation, but now I wrote it as a transformation of Legendre type with these constants. By the way, this is a Coriolis constant, this is this Brandt-Weisshaller constant, and then you obtained the equation of Hoskins semi-geostrophic equation, again in the form which we know very well, and it is not one. That's the point, that you need all these constants in 5 to have a good numerical prediction. You should know the solution with this constant QG and so on and so forth. So if you know this constant, you know potential vorticity. If you know potential vorticity, you should recast this constants, and they want to keep them. What is interesting, that they have many models, again, like in the case of 2-dimension. I don't want to show you all this equation. In some of my talks before, a few years ago, I showed different equation. Fantastically, that to each of them, they can be reduced by various Legendre transformation, always to the form Hessian equal to constant. But the constants are different, and these different constants, it looks strange for mathematicians. Looks strange why people, for example, as I told you in 2-dimension, why people consider these strange values, but for meteorologists it is extremely important. To say the truth, I don't know why. So your question is very good about normalization, but they like it.
And again, if you have the equation Hessian equals a constant, it can be reduced to Hessian equals
to 1. Yes, and for mathematicians,
they are all the same.
Yes, but they don't want 1.
Yes, of course they don't want, but from the you can.
That's the point, that all these models, they can be solved in the same way.
Yeah, okay.
You just have this
Sure.
solution, which this terrible solution. I don't want to say terrible because it is uh, it looks terrible, but in fact it is very beautiful solution, and this solution was uh, uh, rediscovered in some sense in more general setting by Yao and his collaborator a few years ago. It was maybe 10 years ago. They describe a class of equation which have this solution like this semi-geostrophic three-dimensional equation. By the way, I didn't tell you that I'm very proud because this solution, uh, I mean this solution was discovered by two of my students, Bertrand Banos and Oleg Lisovy. They worked together and they discovered this solution, and this solution was first published in the Bertrand's paper with thanks to Oleg. And a few years later, Yao and his collaborators describe a class of equation uh, uh, and class of solutions, and this equation and this solution belongs to this class, and this relates to some string physics models, which I don't want to mention. It was some Calabi-Yau, but anyway. Okay, now I go to another type of application and another type of equation. Anyway, this equation also are related to meteorology or to geophysics models, and it is so-called stably stratified flows. This is quite different models and quite different dynamics and quite different community of people who studied it. So these semi-geostrophic models, it's purely business of Mike McIntyre and his school, and another school in Scotland by Dritchell and his collaborator Viewdes from Glasgow and from Edinburgh. They considered another Monge-Ampère like nonlinear equation which describe the stably stratified flows. Interesting that this Monge-Ampère nonlinear equation, non-constant coefficient equation, but coefficients of this non-constant Monge-Ampère equation, they are a function of another function which can be considered like given potential, and dependence of coefficients on this second function, it is also Monge-Ampère type dependence. Look, so we have the equation 8. This equation has coefficients E, A, B, C, and D. And the unknown function is a big function f with two variables x and z. So for some reasons they don't like y and they like z, okay. And then coefficients are in front of Hessian, it's 1, it's two-dimensional, first two-dimensional. Then A, it's 1 plus small phi xz. B, it's 1 over 2 small phi zz minus small phi xx. C is 1 minus small phi xz. And D is a Hessian of small phi minus var phi. And this phi is a potential which we considered like a given function. And this omega, this var phi, it is what we had a potential vorticity before. Here it is also potential vorticity, but it is anomaly of potential vorticity. For which reason they called it, it comes from this model. Of course, they also consider this Ertel conservation of potential vorticity, and then they study how these solutions depend on the given phi. And it is interesting that it's kind of coupled Monge-Ampère equation. You can play with big phi like unknown function with given small phi, and you also can consider dually equation with respect to small phi, considering big phi like unknown. So first, we want to formulate the theorem which we discovered with Bertrand when we first look at this Dirichlet Wilders equation. We wanted to, of course, it is very complicated non-constant coefficient equation, so we wanted to simplify it. And first, we wanted to write the condition when this equation can be reduced to constant coefficients. It is a kind of condition which we wrote with Valentin in our first paper at 83 on two-dimensional Monge-Ampère equation. And then we discovered that this equation equivalent to symplectically locally equivalent to Monge-Ampère equation with constant coefficients if and only if the Laplacian of coefficient phi is constant and some invariant r, which I will describe in a few minutes, also constant. So this r, in fact, it is Pfaffian. But people also know this like so-called Rayleigh invariant. And then it's happened, of course, that this equation, because it's equation with non-constant coefficient, this equation of a mixed type, it changed the type with respect to the behavior of small phi. And also you can say that what's happened if this second invariant R, this Pfaffian of my Monge-Ampère form, if it is positive, then we can find the coordinates u and v such the form du wedge dv can be written as a holomorphic two form with real part our form omega. Omega, it's a form which corresponds to my Monge-Ampère Dirichlet Wilders equation with non-constant coefficient, and big omega, it's a symplectic form. Square root of r, it's a coefficient, and then we can precisely write these coordinates u and v in terms of initial coordinates. So it's a change of variables. We can introduce u and v by these formulas and the given function small phi. R, it is just a dual coordinate p to x, p to x, and r to z. Then we have this. Then it is, sorry, it is, I miss here, just I can immediately check. And I forgot delta here. Then we can, in these coordinates, we can write this equation like a Laplace equation in terms of phi, of small phi. And Legendre transformation, this gives by this pair of coordinates. So we have this Legendre transformation. And then let's see the corresponding geometric structure. So we have omega dx dp dz dr. Omega, it is, as I told you, just Monge-Ampère form of this Dirichlet Wilders equation. And this Rayleigh constant, Rayleigh parameter, it's nothing but Pfaffian. It can be written in terms of coefficients, of course, like a times c minus e times d minus b squared. And when you have this data, you can write this Rayleigh invariant and our Pfaffian like 1 plus var phi minus delta phi over 2 square. And now, if it is constant, properly constant, like we have here, we can see that the Pfaffian, this Rayleigh invariant, is nothing but this PV anomaly, because it is 1 minus 1, so it is just PV anomaly. And if it is constant, it gives you that d omega equal to 0, and your equation can be, by our criteria with Lichagin, equivalent to constant coefficient. But it is not the end of the story. We can also apply to this consideration so-called hypersymplectic geometry of Hitchin. Namely, we know that if we have four-dimensional symplectic manifold with two forms, with omega, big omega, and Monge-Ampère omega small, then we have a Lagrangian fibration. So in the case when M is a cotangent bundle, it is just means that you can introduce conformal split metric on this cotangent bundle. This conformal split metric can be written in terms of the coefficients of the initial Monge-Ampère equation, and the metric tensor is written like this. And using this metric, we can immediately define the second two form, which dual with respect to this metric to our form omega. So this form defines by just this metric tensor and the endomorphism A sub omega, which correspond to my form omega. And you remember that this endomorphism A omega gives some structure, or symplectic, or complex structure on T star, or product structure. And the integrability of this structure, it is explicitly condition of reduction of integrability of my Monge-Ampère equation. So in coordinates, we can write this form as well in terms of initial coordinates. So we have another equation, you see, dual equation, which gives just by our Monge-Ampère form. And now if we have two forms and this metric, we can just introduce so-called hypersymplectic triple. So we can normalize our symplectic form big omega, dividing by square root of Pfaffian, square root of this Rayleigh invariant, and we have a triple of form theta omega omega with hat, and omega square equal to minus omega hat square equal to plus minus big theta square, and they are pairwise skew orthogonal. It means that wedge product of these forms between them equal to 0. And now I want to remind you few words about recursion operator. Probably you know it, but anyway I should remind. So recursion or Nino-S operator. If you have a pair of two forms, non-degenerate two forms on manifold M, then there is a unique endomorphism, field of endomorphism, big R, which is defined just by contraction of any vector field X with one form, and the contraction, the image of this vector field by this endomorphism with the second one. Here I have some frivolity to write here X like a section of TM, and this field like endomorphism of TM. In fact, it is, of course, endomorphism of section of TM, but I just hope you understand. Now, if I additionally suppose that omega and eta, they are symplectic, it means then they closed and non-degenerate, then we are in the situation which people in integrable systems knows very well, because it's Hamiltonian, bihamiltonian framework, and you have this recursion operator, which or Nino-S operator, which can be used to construct this Leonard scheme and so on and so forth. But I will go to another aspect. We will consider symplectic pairs of form omega and eta for such recursion operator which in square equal to minus identity. This identity endomorphism of Tm. And then the following theorem takes place. If this recursion operator has such conditions that R square equal minus identity on Tm, then it defines integrable complex structure on M with a holomorphic symplectic form big omega, which is just has this small omega like real part and eta like imaginary part. This form is a 2-0 form on complexification of the tangent bundle, which is closed and non-degenerate. Okay, now instead of pairs, we will consider triples, and instead of one recursion operator, we will consider three. So let's consider three symplectic forms on M, two forms, and then we have a cyclic possibility to define for any x and any omega sub I operator R I plus 2. So this definition is mod 3, and it is a substitute contraction with omega sub I, and this is a contraction with omega sub I plus 1. It is a definition of I plus 2 recursion operator, but mod 3 you define 3. And of course, all three, we suppose that all these three defined recursion operators satisfied the condition that they defined or almost complex when R square equal minus id, or almost product structure on M. We suppose that R is not plus minus id itself. And from this definition, of course, it is easy to check that this triple satisfied the cyclic quaternionic relations, that the composition of three R sub I plus 1, R sub I plus 2 equal to id. And now we can give the following definition. If all three recursion operators in square equal minus id, we will speak about hypercomplex structure. In the case when M is four-dimensional, this immediately implies that it is hyperkähler as well. If M is not four-dimensional, then there is a difference between hypercomplex structure and hyperkähler. Of course, any hyperkähler is hypercomplex, but not all hypercomplex is hyperkähler if it is bigger than four-dimensional. And if we have only one R sub I square equal minus ID, then we have so-called hypersymplectic structure. And it is exactly the case of our Dirichlet view, this Monge-Ampère equation. Namely, we can define three tensors. Now it is, instead of I plus 1, R I plus 2, we have IS and T. And I in square minus 1 and tensors S and T, they equal to 1. So there are two almost product structures. And there are these Hitchin hypersymplectic relations between ST and I. Now, we can write also the duplication. So how these tensors appear? They appear from this pair. We have symplectic pair, as I told you, and moreover, we have hypersymplectic triple. Our initial symplectic form and two Monge-Ampère. Monge-Ampère Dirichlet view this and dual. So if we have three forms, we have three hypersymplectic field R. So we have this geometry, and we can write condition on d omega hat also in our condition with Lechagan, which is depend explicitly on the same small phi. You see, so if we have condition on small phi that it is harmonic, then it goes to constant, and the dual also goes to constant. So now we can use this rich hypersymplectic geometry to solve our equation explicitly. Now we suppose that phi is harmonic. Then we have these guys closed, and we have this hypersymplectic condition. So we have integrable product structure, and we can make the following coordinate changing. So introduce this coordinate changing. We write in these new coordinates our forms omega like this. It is just straightforward. And we have for harmonic phi solution L of two-dimensional differential Vudes, and this is a generalized solution if and only if this graph psi satisfy to mixed type. It's like trichomy, you see, with this Pfaffian. If this Pfaffian positive, it's elliptic. If this Pfaffian negative, it's hyperbolic. And S we can completely find from this condition. So what we have linearization of our equation, but this equation linearized using this hypersymplectic change of variables. And of course, it is interesting to consider special case and special case of Differential-Vudes equation when we take constant coefficients initially. What's happened? Except D, which is minus anomaly, this PV anomaly, and then you have two-dimensional equation of nabla plus Hessian equal to anomaly type, and this equation, of course, for some reasons, describes just trophically balanced flow. It means from stratified flow, we can another type of model. So we can do quasi-jastrophic model for special choice of Differential-Vudes coefficients. And the corresponding effective form is this. We can compute Pfaffian, which is explicitly 1 plus this anomaly. And again, you see this PV potential vorticity anomaly sign define the type of this equation defined on this. So in geophysicists, they introduced the notion of so-called dimensionless potential vorticity, and this dimensional potential vorticity, it is just anomaly plus 1. So it is nice for us because if we introduce this dimensionless potential vorticity, it is exactly our Pfaffian. And so in this case, our diagnostic equation in full in this special choice of coordinate gives you the metric G, and this metric G depends on this function. Now this function theta, which is a potential. Before it was small phi, now it's theta, and this metric plays very important role. Now we can play with this metric and play with this constant coefficient dual equation, and so we have the following. So this you see here the Pfaffian of dual equation in terms of any coefficient case, and also the same. This Pfaffian shows that under a good choice of phi and under a good choice of psi. So now it is just because I denote phi, big phi, and psi it was small, and then you can write very well. It is just I gave just computation of some partial solution because I impose in my equation conditions that phi is harmonic, and I proved that it is it gives you reduction to constant coefficients. And I can impose another condition. I take the so-called Legendre dual potential. I take Hessian of coefficient theta equal to 1 in my equation in this. I take theta such that Hessian equal to 1. Then it is possible to use Jorgen's theorem. If we suppose that it is true for the whole plane, then this theta immediately has a polynomial form of this quadratic polynomial plus linear term. And then we can put the computations with the constants alpha, beta, and gamma, and compute this dimensionless partial vorticity, and we will see that it is constant as well. And if it is constant, we have Pfaffian constant, and if it is Pfaffian constant, then our criteria with Lechagin gives you d omega equal to 0. It means that this condition also provides you reduction to constant coefficients. So this geometry is very, very nice. And the last, probably I will not speak about other things, but I want to speak about three-dimensional analog of this diagnostic Dirichlet-Wieldis equation. That it is strange, but three-dimensional analog of this stratified rotating flows, it has absolutely different geometric and differential properties with respect to two-dimension. And of course, it is because in two-dimension Monge-Ampère geometry, it is also quite different. In two-dimension, you have only two geometry, almost complex and almost product. And in three-dimension, you have so-called almost Calabi-Yau three different geometries. And for this three-dimensional diagnostic Dirichlet-Wieldis, it looks like this. Coefficients also are non-constant, and they also expressed in terms of some potential theta, and also in terms of function phi and psi. This function are given, and theta you can express in terms of this phi and psi. So you have big phi, small phi, and psi. Theta it is a psi over sub x and psi sub y. And then it's happened that this complicated equation, you see, with non-constant coefficient has a very simple, from our viewpoint, integrability property. It is linearizable. It is not equation which belongs to one of three nonlinear orbits which we got with Valentin. And this is beautiful for Ferapontov and his collaborator, for Zhenya, Dubrov, Kruglikov, and Novikov. It means that they have a very nice equation, very important in geophysics, and Hitchin-Pfaffian equal to 0, so it's linearizable. And it means it is integrable in their sense. It is a non-constant coefficient integrable in hydrodynamical sense equation, which nobody studied from this viewpoint. And also there is an interesting question about generalization of Pfaffian, because we have Hitchin-Pfaffian, which is 0, but we can generalize two-dimensional Röhrlich invariant, considering these two terms B1, B2, which enter in the description of my equation. You see, B1, B2, they are here. B1, it's a Laplacian of phi minus theta of sub x, and B2, it's Laplacian psi minus theta sub y. And they are coefficients in my equation here. It is very, very interesting invariant. So it is generalized Rayleigh invariant. His role is very clear. It plays the same role like Pfaffian in 2 dimension. It means it's split class of Dirichlet-Wiedius 3-dimensional equation for elliptic and hyperbolic. So it gives you also possibility to write metric corresponding metric by Monge-Ampère form omega, and this metric has matrix of this metric has non-zero 3 non-zero eigenvalues, and this Rayleigh invariant is 1 eigenvalue up to 2, and there are 2 eigenvalues which more complicated, but explicitly can be computed in terms of Rayleigh invariant and coefficients A2, B1, B2, and so on. So proposition which is we proved, in fact I proved that if R bigger than 0, then and signature of this metric is 3, 0, then we have elliptic 3-dimensional Dirichlet-Wiedius Monge-Ampère equation, which is equivalent to 3-dimensional Laplacian. And if R less than 0 and signature is 1, 2, then we have this pseudo Laplacian. We have hyperbolic 3-dimensional Monge-Ampère equation, which is equivalent to this pseudo Laplacian with one plus and 2 minus, or vice versa. And there is interesting open question, and this interesting open question: what is the invariant meaning of this R? Like it was in terms of how we can interpret this. In 2 dimension, Pfaffian had this Rayleigh invariant was what gave you Pfaffian, and Pfaffian was some invariant of your equation. In this case, all our symplectic invariants, they are trivial because Hitchin Pfaffian equal to 0. But this Rayleigh invariant has some mysterious importance, and how it relates to Hitchin, which is 0, or to Hitchin map, which is not 0, and to another. From the viewpoint of geometric invariant theory, this is a mysterious invariant. What it is, I don't know. It would be nice to understand. So here I should stop because it's time, 1 hour and 20 minutes. It's too much time. Questions so far, please.
Hey, thank you, Volodya, very much. It's nice. So questions, remarks here, please.
Hello, Volodya. So I would like to ask about this constants in the 2-dimensional case. There was a constant of square root of 3, and if I understood correctly, the square root of 3 pop out as some geometry consideration, right? Or am I incorrect?
No. It is from some geophysical consideration. There is a paper of McIntyre and Ralston, and this paper of McIntyre and Ralston, they consider some variational approach, and from this variational approach, Lagrangian, they computed some Lagrangian, and they consider solutions of Euler-Lagrange equation in terms of some series, in terms of some developed series, and they consider this series up to 3rd term, and to cut this, they impose some conditions, physically, how to say, they called it physically meaningful conditions. And to have a physically meaningful solution, they imposed some constraint, and this constraint needs that this development should cut in 3rd term. And to cut this in 3rd term, they need some constant equal to square root of 3.
So it's a combination of some
And moreover, they also need some constant to be complex, and they didn't understand how they get this complex condition complexity of for some constant to be complex if they considered a completely real situation. And that was the result of this Legendre transformation. Implicitly, this Legendre transformation changed complex structure on your on your phase space, and they didn't understood why this coefficient appeared in complex form. And it means that when they did this Legendre transformation, they changed complex structure, but they didn't draw attention on it. And then this Monge-Ampère technique was just a kind of simple observation that this Legendre transformation simultaneously change a complex structure on the phase space, and that's why some constants becomes complex in their models. They were very happy with this.
I see. And in the case of the Drichel-Vieudes case and Relic parameter, so is there some relation to that, or is it a completely different approach?
You mean, what do you mean?
So I mean that as you described now, their way of computing the constant.
This two-dimensional Drichel-Vieudes, it is completely, I would say, completely relates to all Monge-Ampère geometry in 2 dimensions. And moreover, as I told you, if you take this choice of parameters, you even obtain from Drichel-Vieudes model, you obtain semi-geostrophic model for this, you see? So this equation which appeared, and also this equation appeared also as a reduction of Euler equation in 2 dimensions. I had no time today to speak about a huge application to non-meteorological but hydrodynamical important models, Navier-Stokes, Burger's vortices, and Euler equation in 2 dimensions. But this equation is typically stream function equation in 2D Euler. This equation. But it is just this. I think it's coincidence, but it is not coincidence physically for geostrophically balanced flow, because the conditions they studied for this rotational stratified, they for this choice of coefficient, they exactly means that this flows becomes geostrophically balanced. So it's a QG choice. Of course, it's just my arbitrary choice to establish this, but generally it is another.
Sure. Thank you.
And about 3 dimensions, it's a very I would say it's a magic case, because equation is quite complicated, but it might be linearized. You see, in spite of all coefficients, Hitchin-Pfaffian equal to 0. And nullity of Hitchin-Pfaffian means that this equation must be linearized. We linearize it with Bertrand in some examples we have, in some examples of coefficients. But how to do it? Because you know this complicated dependence of metric eigenvalues. It's a complicated form, you know. So it's difficult to work generally trying to linearize it. But for some choice, we have some examples of linearization, explicit change of variables, I mean.
Okay, more questions, remarks, questions? No remark, no question. Volodya, thanks a lot. It was interesting. So come to Moscow, get your vaccine here, and we meet next Wednesday at the same time with the talk by Maxim Pavlov. So thank you for visiting the
He
seminar.
will speak about what?
Well, have a look at the seminar page. It's written there.
Unfortunately, next week I start again to teach, and sometimes my Wednesday class just overlap with the seminar. I don't know.
Variational principles for some one-dimensional gas dynamics, and for Yegorov, hydrodynamic type equations.
Ah, okay.
Well,
But probably he will have slides.
yes, surely. Of course, he will speak.
Yes, if you want my slides as well, I can send you.
To Alek.
To Alek. Okay.
Ага.
Okay.
Да, пришлите,
Bye.
пожалуйста.